Hello everyone, my name is Medha, and today I will be talking to you about my senior research project, Modeling All India Rainfall Using Big Data, a response to recent global climate changes. All India is a term used to refer to all of the rainfall over the country of India specifically, not the entire Indian subcontinent. Now what will I be doing in my project? Well, there are two overarching goals. First, I want to make accurate predictions of the future all India rainfall during the monsoon season, which is June, July, August, and September. And the second is to predict any anomalies that might occur in the near future. To do so, I will need to develop a formula for a model that will predict the rainfall levels for that year. Ideally, this model will be able to make accurate predictions for the next decade or two. So why is this important? Approximately 17% of India's GDP relies on agriculture, and much of it takes place in areas that are prone to flooding. Variations in rainfall of just 10% between expected and actual rainfall can cause severe flooding or drought, drastically affecting Indian food production. This means millions of people in a country already experiencing great rural poverty won't make enough money to sustain their life. My research is based off of a paper written by Dr. Bin Wang, titled Rethinking Indian Monsoon Rainfall Predictions in the Context of Recent Global Climate Warming. In this paper, he focuses on the Central Pacific El Niño Southern Oscillation. This term is used to describe the strengthening of North and South Pacific highs and the accelerated deepening of the Asian low that occurs during the boreal spring season. He believes that by focusing on this oscillation, we can accurately predict monsoon season rainfall for all India. So, to begin my model, I first had to read Dr. Wang's paper. In it, he talks about 4 predictors he believes will be highly correlative in building a model that predicts all India monsoon season rainfall. These 4 predictors are EPT, CPT, PSH, and NAT, the first 3 being based on the El Niño Southern Oscillation, ENSO for short. EPT and CPT are built with sea surface temperature data. Sea surface temperature, SST for short, is critical since ocean temperatures influence rainfall patterns throughout the world. So when SST changes, so do the rainfall patterns. Increases in SST lead to an increase in the amount of atmospheric water vapor over oceans. This water vapor feeds the weather systems that produce precipitation, increasing rainfall. PSH and NAT are built using sea level pressure, SLP for short. Air rises in low pressure areas and falls in high pressure areas. In a low pressure area, the rising air cools, and this is likely to condense water vapor and form clouds, consequently rain. The opposite is true in high-pressure areas, which tend to have cloudless skies. All of these predictors are built by taking the data over specific geographic coordinate boxes. These are correlation maps of the boreal summer anomalies, June, July, August, and September, with respect to the 3 ENSO predictors. To build each of these predictors, I subtracted the data of one coordinate box from the other. These contour plots are taken from Dr. Wang's paper. For these plots, the blue to red scale is the only one that matters as all of our geographic coordinate boxes are over water. Dark red means a large positive correlation and dark blue indicates a strong negative correlation. Once I built my 4 predictors, I ran each of them individually against my precipitation data to find the general trends. EPT, CPT, and PSH all have a positive correlation with all India rainfall. It is a bit hard to tell with NAT, so I ended up using code to find the slope of the line, and it turns out that NAT has a negative correlation with all India rainfall. Just to specify, all of these were run against rainfall during the monsoon season, which is once again June, July, August, and September. The next step in my process was to run multiple linear regression. I made these plots just to verify that the 4 predictors didn't impact each other too much when running the multiple linear regression. It was important that all 4 predictors were independent of each other. Dr. Wang determined his training period to be 1900 to 1988, so for the initial steps of generating my model, I decided to stick with his training period. Using multiple linear regression, I was able to generate coefficients for each predictor to create a formula that would generate a graph. I was able to obtain Dr. Wang's model from his paper. He had a picture of his graph, and I used a webplot digitizer application to convert his graph into a CSV file full of points on his graph. Using the CSV file, I plotted this graph against my model on my Jupyter Hub interface. As you can see, both models are incredibly similar. This meant that I successfully completed my first few steps of my research project. This plot is my model against all India rainfall during the monsoon season. As you can see, the graphs line up moderately well during the training period of 1900 to 1988. The next step in my process was to run a cross-validation on all of these predictors. This time, I didn't limit myself to the training period. I ran a leave 30 out cross-validation, which is based on the leave 1 out cross-validation method, on all of the data from 1900 to 2018. Through this, I was able to find new coefficients that were statistically significant and took into account more recent climate changes. All of the predictors have a 95% confidence interval that is incredibly small, which is good news. Since the 1980s, rainfall patterns in India have changed quite a bit, and this longer time period allowed these changes to make an impact on the coefficients for the variables. This graph is just a comparison between the cross-validation method I created and all India rainfall. While the model doesn't match up quite as well to the data early on, its accuracy to the data post-1960 is much higher. Once these steps were over, it was time for me to find new variables to add to my model to increase its prediction accuracy. Initially, I ran a simple cross-correlation between variables, such as the DMI index, which is an indicator of the east-west temperature gradient across the tropical Indian Ocean, linked to the Indian Ocean dipole. After running multiple different climate indices against all India rainfall data, I didn't find any climate index that produced statistically significant correlations. After talking to my external advisors, Dr. Boos and Dr. Ramesh, we decided to explore moist static energy. Dr. Boos had written a paper about MSE in 2013 and thought that it might prove to be useful for my model. MSE is a thermodynamic variable that describes the state of an air parcel. It is similar to the equivalent potential temperature. This contour plot represents the contemporaneous correlation between MSE and AIRI. As you can see on this plot, there is a dark red patch in the northwest part of the Indian subcontinent, with a high correlation to all India rainfall. Not only did the MSE produce statistically significant correlations when run against all India rainfall, but it also changed my model quite a bit during my initial incorporation of MSE into my formula. I hope to explore MSE's correlation to all India rainfall more. Another aspect I began to look into was how Dr. Wang built his models in the first place. For most of his predictors, he had this unique feature of subtracting the March data from the May data to build his predictors. Most models rather take the mean of the March, April, May data to build predictors, as a subtraction of data is not a very traditional method for building predictors. After taking a closer look, I made some interesting observations. For sea level pressure, just like Dr. Wang noted, there was a larger correlation to all India rainfall in the May minus March plot as opposed to the March-April mean contour plot. This is indicated by the geographic coordinate boxes I drew on both contour plots. These are the boxes from which I used SLP data. For SST, however, it seems like the March-April-May mean, in fact, has a higher correlation to all India rainfall than the May minus March data. This can be seen by just comparing the coordinate boxes on each contour plot. This was an incredibly interesting discovery, as the May minus March datasets were a unique feature of Dr. Wang's model, and it seems like that wasn't improving the model's accuracy in terms of sea surface temperature. With this being said, my 10 weeks of senior research came to an end. I was able to successfully create a model that replicated the likeliness of Dr. Wang's model initially, and then improve upon it with cross-validation over a larger data period. I wasn't sure if I would be able to find another variable that had a statistically significant correlation with the all India rainfall monsoon season, but I was able to find out that MSE did. My last result really shocked me, as I didn't expect to find out that the March, April, May mean data had a higher correlation to the monsoon season rainfall than the May minus March data. While I wasn't able to incorporate these new findings into my model, I have decided to continue my senior research project into the summer. I hope to improve my model to incorporate moist static energy and implement the March, April, May mean data period for SST. I want to publish it online for others to take a look at. I also hope to write a short paper on my research findings and have it published by an environmental science journal. This model will allow for more accurate rainfall predictions, providing people with warnings before changes in precipitation and giving them time to adapt and prepare. I strongly believe that once I have finished building my new and improved model, it will be able to make predictions for the next 2 decades. This model has the potential to prevent mass economic losses. It is important to note that this model is able to make predictions for a particular year's monsoon season rainfall with the SST and SLP data gathered during the March to May period of that same year. With that being said, I just wanted to thank my internal advisor, Dr. Beck, for helping me with this project, and my on-site advisors, Dr. Boos and Dr. Ramesh from UC Berkeley's Earth and Planetary Sciences Department. Thank you for listening.